Okay, so today we'll be discussing the week 8 lectures. So we are having, like, we have the topic floods and tsunami. So without further ado, I'll start presenting, and hopefully participants will join in the meantime. Okay. So, as I said, this is the week 8 problem solving session, and we'll be discussing the topic floods, and if time permits, we'll also discuss the topic tsunami. So, the what do you mean by floods? Like, people across India, especially during the monsoon season, most of the places which get the proper rains for a long period of time, they are prone to flood events. So basically, what we have to understand is that almost like 70% of the earth's surface, it is covered by water. And everybody, like, be it humans, be it plants, be it different variety of animals, everybody requires this water, and water is necessary for their survival, so it is extremely important. So what happens is that in situations such as flood, this same water, which is necessary for our survival, poses a threat to life and property. So, excess of anything creates a problem. So, here, excess of water is creating a problem. So, a flood will happen when water overflows or immerses land that is normally dry. So, all of us might have, like, definitely we have seen the wells, we have seen the rivers, we also know the sea, we know the lakes. So, in all these situations, the water is contained in a particular area. For instance, like in case of river, it is contained within the river channel. Well means within that well we have the water. So lake, a particular area is consisting of the water and not more than that. That is the normal condition. But what happens is that when the flood happens, so this natural boundary that that particular water was staying in, the water will overflow that boundary. So when water overflows or when it immerses the land which was initially dry, we say that we have a flood event. So this occurs when the amount of watering entering a stream, either due to the rise in groundwater or heavy precipitation, result in surface runoff, which causes an increase in stream level as compared to the channel capacity. So this is what I was talking about. Like basically, um, okay, I don't think I have the option to draw on the slide. Um, Anyway, I think what is written here and what I'm going to explain will be sufficient for you to understand. So basically, what they're saying is that a stream, okay, I'll just draw it and show. Just a moment. Okay. So, what I'm trying to say here is that let's say you have a stream like this, okay? So, this is a stream of water. So, and we have land over here on either side. So, what happens is that when this stream, whatever water is coming into the stream, that increases due to a rise in either the groundwater, which is like basically as the name suggests, water stored within the ground, or if continuous heavy precipitation is happening, like rain is continuously falling. So, in such situation, what happens is not all the water will be able to be contained within this channel, and also not all the water will be able to go into the ground. So what happens, the excess water whatever is present will overflow in the form of surface runoff, which causes an increase in the stream level as compared to the channel capacity. So initially if the stream was able to be contained within this boundary, when water increases it will not be able to uh, be contained within that, and then water will overflow. That is the condition that is mentioned over here. So this brings us to the next question, like, is flood a natural process? So okay, I can explain the previous slide. I just started it. Just a moment. So I was just basically telling why water is necessary. Like 70% of the Earth's surface is covered by water, and as we all know, water is essential for the survival of all kinds of living beings. So, like be it humans or animals or plants, everybody requires water. But when a situation arises where this water poses a threat to life and property, we refer to it as flood events. So a flood happens when water overflows or immerses the land that is normally dry. So I had drawn here showing a stream with this to be its boundary, and we say when the situation when flooding occurs is when there is excess of water entering into the stream. This can be due to either a rise in groundwater level, or it can be due to heavy precipitation, either of the thing or both. Anyway, that results in an excess of water, and that excess of water is not the stream is not able to contain it within the channel, so the water will overflow. So it is exceeding the channel capacity, and then we have the flood event. So this brings us to the question, like, is flood a natural process or is it a hazard? So hazard is when it poses a threat to life and property. But we know that flooding is also like rain is something which keeps happening. So flood is inevitable. So like that there is this confusion between whether it is a natural process or a hazard. So it is a natural process. So in order to maintain equilibrium, which becomes a hazard when people choose to live and work in flood prone areas. So with increase in urbanization, the number of flash floods and higher flood levels have increased across the world. So essentially, this flood which we see around us, that is a natural process. So rain comes, and when the channel is not able to hold it, it overflows and flooding, because this is a natural process. But it becomes a hazard when it poses a life threat to life and property, when people choose to live and work in flood prone areas. So as if you remember from previous sessions, I had mentioned that people choose to live, especially from the past, it has been noticed that civilization has mostly been found on the floodplains. Why? Because it is more fertile, and people find it a better spot where they can do agriculture. So that is the reason why people choose to live in such areas. But the problem is that during a time of heavy precipitation or excess of water coming into this river, then this river will overflow, causing flooding and essentially affecting this agricultural lands and people. And nowadays urbanization has significantly increased. Like there are a lot of cities, towns, and a lot of buildings, which has resulted into a number of flash floods and high flood levels across the world. So the flood causing factor, so what causes flood? So we have two, like we can divide it into two. So the first one is the primary cause, and second is the secondary cause. So the primary cause is the intensity and duration of rainfall, which I had just mentioned. So when you have heavy rain or brief torrential rain, so heavy rain is like continuously a lot of rain is occurring, and brief torrential rain is when this that is kind of a heavy rain, but which happens for a very short period of time. Kind of we can say like a cloud burst. Then tropical cyclone. So coastal, like people from coastal areas might have experienced this. So when tropical cyclone occurs, the heavy winds are also a problem, and at the same time, the water accompanying that becomes a problem. Then the seasonal monsoon rain. So these are the primary causes of rainfall uh, in across the world, as well as especially in the Indian scenario. Then the slope is another thing. So the depending on the slope, the flooding can occur. Like if it is excess of slope is there, the water will flow, and if not, the water can stay. So that kind of thing. Then the soil properties. Soil properties is basically porosity and permeability. So what kind of soil is present? If the soil has a lot, it is highly porous, and if it is highly permeable, permeability is basically how connected these pores are. Okay, so like how easily that water can move within that material, like the soil layer. So if the porosity and permeability is high, then the water can easily percolate, but if not, the flooding can occur. Then the river dynamics, like how the channel, the width of the channel, the region surrounding the river, the channel bed, like what kind of material is there. So all these things will kind of dictate whether that area can become prone to flooding or not. So these are primary reasons. Then comes the secondary ones. The secondary one is dam failure. So if, for instance, there is like that dams hold a lot of water, right? So if the dam fails, then what happens? All of a sudden, a huge volume of water is released. So that can result in flood. Then ice jam. So if ice is present, it's kind of like this dam effect. So if water, like ice is there, and then see, when it melts, then also a significant amount of water is incorporated. Then comes river breach. That is basically, as I said, river always flows within a channel, and when excess of water comes, so and if it just comes out, then that is known as river breach. So that way it can happen. Then human induced is kind of similar to the dam part. Like if people knowingly or unknowingly, like during heavy rains, if they don't open the dam at the right time, then what happens, like if they create a delay in opening the dam, then a human induced flood can occur. So such several factors are there which causes the flood. So the water, this is basically what happens is, first the primary requirement is what? We need water, right? Uh, so when water, either in the form of rain or snow melt that comes, so that will, at first what happens is you have a soil like this, okay? Let's say this is a section. So first water is coming down, either in the form of rain or in the form of snow melt. First it will infiltrate into the soil layer. So that infiltration, like whether how far it is going or how long it can go, that depends on the soil characteristics as well as the geology of the area and vegetation present. So if there are a lot of trees present, their roots will take a lot of water. So which in turn results in the soil's ability to retain more water. Then the geology of the area, like how whether there are fractures present or what kind of rock is present, that dictates. And then the, as I said, characteristics of the soil, that is porosity and permeability. So first it infiltrates, then it percolates through the soil based on its property. So if it is highly porous, runoff will be less, so the soil can hold a lot of water. If it is less permeable, uh, basically it is not able to move within the soil, so it will overflow and there will be more runoff. Then we have the topographic influence, which is basically if you have a steeper gradient, that is if you have a steeper slope, the runoff will be fast, and will not have time to percolate into the soil. But if it is gentle, then the runoff will be slow and the water will have more time to percolate into the soil. So these are several once it rains, this is how the water is managed, and if it is not able to be managed properly, then flooding will occur. So this is a small video regarding this topic, so you can just have a look. This was just basically a video telling you about the causative factors of flood in the current scenario and general things. So I just wanted you to see the visual thing. That's why I had put this video. So, in order to understand flooding events, it is necessary to understand the processes by which rivers transport water and sediment. So, I've been, I have kept telling you about this channel capacity, the river. So, all in order to have a grasp of flooding in different kind of rivers, we need to understand how the river is transporting the water and it is transporting the sediment. So this is basically the river dynamics. So we need to know the river dynamics. Now you have to understand that rivers, it's not a plain simple thing that river come from the mountains and it brings a lot of water and sediments. That's not the only thing. Rivers are complex systems and they have a lot of interconnected channels and they have many tributaries which flow to one major river. So like the rivers like Ganga, Brahmaputra, so right? They have a lot of tributaries. Tributaries is basically what? You have one main channel of river and then a small rivers joining into this main river. So these are the tributaries. Okay, so the rivers are complex systems. They have a lot of interconnected channels and they have many tributaries which flow to one major river. So what these rivers what happens is that they respond to the regional climate and weather changes through varying flows and sediment particle size and amount supplied to channels. The basic understanding is that now if you take a look at India, so the southern tip of India receives this monsoon right first. So this area will have a lot of rain uh, effect. Like the rivers over here are more prone to flooding because we have the western ghats over here, lying alongside the coast. So this area is not that prone to flooding because of this monsoon rains, but then because of cyclones this area can receive a lot of water and result in flooding. So that way in within India itself we have different regions which experience different intensity of this monsoon. So the region which has a lot of rain coming in, like the initial part and the core monsoon zone within the central India, those areas this flow can vary very quickly. The sediment particle size as a result of the flow can change, and as a whole this can result in flooding. So the river is a very complex system and understanding river dynamics is very much important in order to understand the flooding nature of that particular river. So first you have to understand stream flow. So flow generally increases downstream. Downstream is basically if the river originated from this region. So this is the downstream direction. Okay, like let's say this is a mountain, so this is the downstream direction, and this is the upstream direction. So flow, as in a general scenario, the flow will always increase downstream, because water from tributaries are also coming, and also the groundwater level might vary as the like in the downstream direction. So for every river, like each river has a watershed or a drainage basin. That is basically an area of land that drains all the streams and rainfall to a common outlet. So if you, I think I had shown an image of river Kosi. So it's basically, this can be said as the watershed or drainage basin for that river. So you will have the river and its tributaries, and this entire area is the region where the streams they drain all the water uh, to this common outlet. So you can see in this image also an area of land wherein all water that enters it either through precipitation or springs drain to a single point, such as lake or the ocean. So this entire area can be called as the drainage basin for this particular river. So stream flow we discussed. Now we need to know the stream discharge. Discharge is the total volume of water flowing per unit time. So like say per minute or per hour, whatever. So how much water is flowing per that particular time. And that is measured using the acoustic Doppler current profilers. So this, I don't think you will require this much of mathematics. This is just for your understanding. And if any problems like is asked in order to, like they give you the average velocity and area, and they are asking you to find the discharge or total flow, then it is essentially a product of velocity and area. So this is the discharge or total flow, which is given in meter cube per second. That is what I was saying. Meter cube is the volume and second is the unit time. So the flow per unit time, and that is how we are getting it. We are multiplying velocity into area. And area, as you might be knowing, it is, you will get it by width into depth. So this I just put it here because if you have any numerical problems or something, so you'll know the like the formula, and then you can apply it. So this is a subsection that they have shown here. This is a river. So they took a cross section over here, and if you just consider it in this small segments, so this subsection you can take the depth and the width of the section, so you will get the area, and then area into velocity will give, for each subsection you will get the discharge, and then if you add it together you will get the total stream discharge. I don't know if sir had mentioned this, but it is a useful thing for you to keep in mind when learning about flooding events and discharge and all those things. So as I said, we need to understand the flow in the river, and also we need to understand how the sediment is moving within the river. So that brings us to the topic, the sediment transport and stream equilibrium. So along with the water, so it's not just water which is coming into the river. So when the water comes, along with it, the rivers are also carrying sediments in the downstream direction. So there needs to be a equilibrium which has to be maintained. So the sediment inflow and outflow is in balance and maintained by the stream. So whatever sediment is coming, it is not that when there is a lot of sediment coming, that is accumulating. So the river will find some way or the other to maintain that equilibrium. A dynamic equilibrium is always maintained. So the stream gradient is basically the slope. Okay, so if that steepness with which the stream descends from its highest elevation to the lowest. So as I had said, most of the rivers or streams, they originate from the mountains. So the gradient is changing as the river flows. So in our particular case, if we consider Ganga and Brahmaputra and all, So that is originating from the Himalayas, and then they are coming down into the plain area. So we have the Indo-Gangetic plain. So in that plain, all the rivers are coming. So as we move downstream, the stream discharge will increase and sediment size will decrease. And finally, it reaches the base level where no further erosion takes place. So the path in which the river is moving, that is continuously getting eroded. So that's what I was saying. Like, although the river is bringing a lot of sediments, but at the same time it is taking out a lot of sediments. So there is a dynamic equilibrium which is maintained. If you have any doubt, just stop me, okay? I'm just going forward and thinking that you're understanding what I'm saying. Okay. So pronounced erosion, that is significant erosion, will happen in the steeper regions, and as gradient decreases, deposition supersedes erosion. So what it is telling is that, let's say uh, this is a mountain and the river is flowing down the mountain. Okay, so this is the plain area and this is the mountainous area. So when the river is flowing in this area which has a lot of slope or steep, what happens is the river will flow fast, right? So when it flows fast, it can erode easily whatever material is there in its path. So here the chance of erosion is more. But as the river comes to the planar areas, erosion will become less and deposition, that is whatever material it has taken from the top area, starts depositing at this bottom area where the gradient is very less. So that deposition usually happens in the form of an alluvial fan. Okay, so that is a triangle shaped deposit of gravel. Gravel is basically the bigger size particles, then sand and smaller materials like the mud or clay, which together we call it as alluvium. So gravel, sand and smaller particles which is brought by the river, we call it as alluvium, and that deposits in the form of alluvial fan. This is kind of like the fan that you might have seen, right? People holding to like during hot weather and all. So that kind of fan shape this has, and we call it as the alluvial fan. So whatever sediments the river is bringing, it deposits it in this alluvial fan, and that material is known as alluvium. So if we take a look at this, this is a front view, you can say. Here you have the alluvial fan. Okay, this entire thing. So the highest hazard area is at the apex of the fan. Apex is the this top portion. Like if you have the fan like this is the apex, and this area is the toe. Okay, so the most hazard prone area will be the apex, because there still some higher velocity flow can happen. So entire flow is concentrating over here, then the hazard becomes less as the flow spreads out. So from here the flow is spreading out in this fashion, right? So the hazard rate becomes less. So if you consider this as the high hazard area, then you have the moderate, and then as you approach the toe of the alluvial fan, you have the lower hazard area. However, the path of the flow may change to concentrate on different parts of the fan as it finds the easiest way down the slope. So the problem is that, not problem, the thing is that not always it is going to happen in this uniform fashion where river is coming like this and then it is spreading like this. At times it will take a path which is more easier for it to flow depending on what kind of geology is there. So that can vary, but most of the time when you have an alluvial fan, the highest hazard region will be close to its toe, I mean apex, and the lower hazard region will be towards its toe. So as I said, the sediment size, the sediment load, all these things plays a role. So the sediment size and the amount carried by the stream depends on the velocity as well as the volume of the flow. If the velocity is high, then sediment, it can even take big rocks with it, right? Boulders, that can be brought in. But if the velocity is less, only small fragments can move. That is what it is showing over here. So greater velocity is required to mobilize the particles than velocity which is required for transportation, because once the material is there, comes to the flow of the water, then it can be easily transported. But if it is just staying in this river bed, and you just have to lift it up there, a lot of velocity is required. That is why in higher velocity areas you can see bigger particles. That is what is over here. Erosion happens. Particle size, you can see, here deposition happens and the particle size is like this. So as the particle size increases, like particle size increases with the flow velocity. So there is an optimum balance between that, where it erodes and where it deposits. So if you take a look at this, the grain size decreases downstream as slope decreases in the stream channel. So here you have a bit of bigger particles, and as you go down the slope, the finer grains are more, like you find more finer grains. So this first image, it is a turbulent, high energy Loxa River in the mountains of northeast Idaho. This has a steeper gradient. That's why you can see that that turbulent flow over here. That white part is showing the turbulence. But then if you look at this, you see the Smith River, which has a lower gradient, so it looks very calm, and also it will carry finer particles. Here you can see big rocks, right? But here it will be more fine. So that is the difference. If you have a higher velocity at the higher gradient, then you will have big particles, and when the gradient is less, you have finer particles and the river is more calm. So when sediment load or volume is high, it will exceed the carrying capacity of the stream. So the excess sediment will get deposited on the channel. So let's say the river is coming like this, and the sediment load is increasing. So the river channel has a capacity, and beyond that capacity, if it has a lot of sediment incoming, then what happens is the excess sediment will deposit on the sides of the channel, as well as within the channel. So it deposits it rather than it going with the flow. So the carrying capacity depends on the stream discharge. Like if stream discharge is high, it can carry a lot of sediment, but like in case of a flood event. But if the stream discharge is low, then the sediment load that it can carry will be less. Please stop me if I'm going fast. I'm just thinking that you are understanding what I'm saying. That's why I'm not halting in between. So, as we had discussed, flooding is a natural process by which rivers move sediments to maintain equilibrium. So, that is a natural process. But when velocity is low, all the materials brought into the stream will stay put. Velocity is low means that material is slowly moving, rather like it is not moving in further distances. But during flood, when the water rises, the accumulated sediments will go in the downstream direction. A lot of sediments will go in the downstream direction. During a flood, the stream can carry larger materials. Coarser particles gets broken down and flushed downstream. So let's say this river doesn't normally host a lot of big particles, but if this river floods, or if flooding occurs, then that water can bring in big rocks and all kind of materials. That's why after a flood event, when the water recedes, you can see a lot of these mud. Along with mud and clay, you can also see big chunks of rocks and everything present, which earlier might not have been. So when geologists or geomorphologists or sedimentologists for that matter, when we study an area uh, and we see a section of let's say a lot of fine particles are there, and then suddenly a section is there where you see big pebbles or cobbles or whatever it is, then that kind of tells you that that river had experienced a high flow event during this time. So if you date this section, you will know in what time in the past that area experienced flooding. So this big particles are an indication of flooding. So here you can see, as the description gives, giant granite boulders dumped by a landslide into the Feather River in Sierra Nevada can be moved only in an extreme flood. So these boulders were dropped over here by a landslide event. So you know during landslide, a huge bulk of material is coming down. So it got dumped over here in this river channel. Now only uh, an extreme flood event where excess of flow happens, only then will these boulders be moved from here. Otherwise these will stay intact because they are very heavy. So a lot of excess of flow and velocity is required in order to move these boulders. Just give me a second, I just want to drink some water. Okay, so now we will be discussing about the channel patterns. So as I said, all rivers are not the same. Their channel shape can vary, right? So always ideally we will we'll be talking about a river channel in this manner, but this is not the case. It can change. So it can either be straight, it can be meandering. Meandering is this curved thing, or it can be braided. Braided is basically you know you will have sand bars like this, so river will have to flow like this. So it's kind of like a braid, how like women braid their hair, so it's kind of in that fashion. So river channel can be either straight, meandering, or braided. This is a broad classification. So in case of straight channels, they are very rare. Not that is kind of like an ideal condition. So it's not always possible. It's a rare thing. It is always confined by topography or follow geological structure. So if you see a straight channel, you have to understand that some kind of geological structure like a fault or a joint is present over there, because uh, faults or joints are more or less linear in nature. So if a fault is present and some path is there, the river can flow in a straight channel. Now, even in straight channel segments, water flows in a sinuous fashion. So, although the channel is straight, although channel is like this, water will flow in this manner. That you have to understand. Just because this channel is straight, water will not flow in a straight fashion. It will move in a sinuous fashion. So, the deepest part of the channel, uh, let's say this is a cross section, so the river is coming like this, so this is a cross section that is shown over here. So this deepest part will experience highest velocity, while this side, so it's kind of like in this manner. So here it experiences medium velocity, and here it experiences low velocity. So in three zones you can change. So this is the high velocity area, which is the deepest part, followed by the medium velocity, and then followed by the low velocity. So even though the channel might be straight, the river will always flow in a sinuous fashion, where the deepest or the highest velocity part is in the middle. And as I said, the meandering channels sweep from side to side in wide turns. So it's kind of, very extreme. This you can see here, right? So this entire river channel, if you see, so you can see it is extreme turns are there over here. Okay, like this. So these are called meandering channels, and these are the most common. So most of the time, when you draw a river or something, so you might be drawing it in this fashion, and that is basically because most of the rivers that you see are meandering in nature. And these are typical of wet climates and consist mostly of fine grained sediments. So it's the flow is not very heavy, because of which you find a lot of fine grained sediments, and most of the time we see this in the wet climatic region. So in tropical climates like in India, we can see in the Amazon rivers, most of they are like this. So this is most common, unlike straight channels, which are a bit rare. So these are located on flat terrain, because of which the flow kind of reduces. So like if it had been on a slope, so the water can just come down easily. So the channel most more or less might be straight in nature. But if like in case of meandering rivers, they are found in flat terrain, because flat terrain reduces the flow speed, and when the flow speed is less, the river will meander. It will not be able to go in straight path. So depending on that flow, it will meander. And the one which I said, no, like this deepest part, that is known as the thalweg, which is the deep and high velocity part of the stream. I know there are a bit too technical terms that I'm discussing, but that is just for information's sake. You just have to focus on those parts which sir had mentioned in the lectures. So I have tried to include that plus some more just for information's sake. So the erosion on outside part of the bend and deposition happens on the inner part as point bars. So in this direction, in this image you can see erosion will mainly happen on this outer part over here, and deposition will happen over here. And these deposited thing we call it as the point bar. That is what is shown over here. So meanders close together until floodwater breaks through the narrow neck, creating an oxbow lake. So when does an oxbow lake form? So what happens is that, let's say this river was going like this, and when uh, some amount of flooding occurred, excess flow happened, then the water will cut and go like this. So what happens is this section which is there, that gets isolated, and it becomes an oxbow lake. So here I have a video describing that, so you can just watch it.
The meandering rivers of the plains may seem tame and lazy, but models turns out
So that kind of gives you a visual idea regarding what an meandering channel is, how it flows, and what an oxbow lake is. Uh, so that brings us to the next, the third type of river channel, which is the braided channel. So the braided channel, unlike this meandering or straight channel, it has multi-channel paths. So here you can see how sophisticated it is, right? So it can move in this fashion. Here you have a channel path. So it's very diverse, you can say. So it's multi-channel. And this is less common. It's not as common as the meandering channels, but compared to the straight channels, they are a bit more abundant. So this is common in dry climate. So that you have to keep in mind, okay? Meandering channels you mostly see in the wet climate, while braided channels you mostly see in the dry climate with abundant coarse sediments. So this is the difference you can point out regarding the meandering and the braided channel. Meandering channels are more common in wet climate and has abundant fine sediments, while the braided channels are common in dry climate and has abundant coarse sediments. So the streams get overloaded with sediments that are deposited in the channel. So a lot of coarse sediments are there, making the water to shift to one or both sides of the deposit. So what happens is, as I said, let's say this is a straight channel, and in order for this to become a braided channel, what happens is a lot of this material gets deposited in this small pockets, you can say, and then water will flow in these multiple paths or channel fashion. So this is formed in steeper slope or where the stream is entering from steeper to gentler slope. So broadly, if you see, let's say this is a mountain, okay? So, and it gradually becomes gentler and then it becomes plain. So we can say that the chance of finding straight channels are more over here. Then comes the braided, which is found mostly in gentler slopes. And then as you approach the planar areas, you find the meandering channels. So that like as a whole, you can just imagine in this manner, but you have to keep in mind braided channels are mostly found in dry climate, while meandering channels are mostly found in the wet climate areas. Now, what are gaining and losing streams? So gaining streams are those which are fed by groundwater. Okay. So gaining stream is what? A stream already has a water, and then water is supplied to it by the groundwater. Like increase in groundwater level will also supply to the stream. So we call it as the gaining stream, which is fed by the groundwater. Now, when the stream loses its water to the ground, then we call it as a losing stream. So water is decreasing in the stream because it is going to the ground. So groundwater level will be higher than most stream in areas with moderate to high rainfall. So regions experiencing moderate to high rainfall, they will have the groundwater level higher than the stream level. So streams will get continuously fed, ensuring year-round flow. So the thing is that in such regions which has moderate to high rainfall, the groundwater level will be a bit higher. So during rainfall period, the rainfall will feed the stream, but even in the absence of the rain, because the groundwater level is high, that will feed the respective streams. So we have gaining streams. But losing streams are mostly characteristic of drier climates, because what happens is that the groundwater level will be less. Okay, so already rain is less in such areas, and because the groundwater level is low, the stream water will percolate and will be feeding the ground. So they flow primarily after a rain and may dry up in the absence of rain. So they are, we can call them as ephemeral rivers. So only during rain time it will flow, and other times they will remain dry. So they are losing streams, gaining streams and losing streams. So I think sir has also mentioned this, so that you have to understand what is the difference between these two. So here I have an image showing this. So this is the wet climate thing. So you have the water table which is above the um, stream, this is the flow. So above the stream flow you have the water table. So in wet climates, groundwater flows into the gaining streams. So water will flow and supply, always it will maintain a flow in this channel. But in case of dry climate, you can see the groundwater is below the stream level. So what happens in dry time, or when the rain is not there, water will go into the ground, thus leaving the stream more or less dry. So only when rain is there, the losing stream will have a significant amount of water. But when rain is in the absence of rain, the losing stream will not have that much water, because the water is going to feed the water table, groundwater. So that is the main difference between the gaining and losing stream. So you can maybe draw a diagram like this if you have a descriptive question, something like that. So upstream and downstream flood. So you know what I had mentioned, right? So if this is the direction in which the river is flowing, this is downstream and this is the upstream. So what do you mean by upstream and downstream flood? So upstream flood affects smaller area, and that is localized and caused mainly by cloudburst or dam failure. So cloudburst is what? A torrential rain, a lot of rain in a small period of time. So during such scenarios, the upstream regions of the river can be flooded, and like people staying there can experience flooding. This occurs for a very short period. It doesn't happen for a longer time. But downstream flood, it affects a larger area, and that is caused mainly due to prolonged heavy rainfall in the upstream. So instead of a cloud burst which happens for a short period of time, if you have continuous rain for a long period of time, then what happens? Excess of water will be there, and that water will flow down and flooding the downstream area. So this affects a larger area as opposed to upstream flood, and this happens for a longer duration. So this is the difference between upstream flood and the downstream flood. So such differences, like if you are asked to differentiate between these things, so you can just write it in this point manner. So the smaller area factor, area wise you can say uh, the duration of that water supply, those things you can say, how long the flooding is supposed to happen. So we have already discussed about the different types of drainage channels. Now you need to understand the drainage patterns, like how like each river, each major river has different kind of drainage pattern. So what all kinds of drainage patterns are there? So the first one is the dendritic drainage pattern. Okay, so dendritic, that is kind of indicative of tree branches, right? Dendrit. So dendritic is what? Basically it is found in homogeneous, gently, not dripping, it is dipping. Okay, so gently dipping strata. I'll just correct it. Okay, so that is gently dipping strata. You can say a bit planar or something like that, and you have a branching pattern in different direction. That is what is shown over here. So you can see the flow, right? So this is the main stream, and the tributaries are joining. So it looks like a branch, a tree branch. So the subsurface geology has a similar resistance to weathering. So there is no apparent control over the direction of tributaries. Because the subsurface over which this river is flowing is more or less similar, so it can flow in any direction. Like it can erode in any fashion. So that's why we have this branched kind of structure. and all the tributaries which are joining the mainstream. So if this is the mainstream, the tributaries are joining the mainstream at an acute angle. Acute is what? Less than 90 degree. So that is how they are joining. That is what dendritic type of channels are. Okay, I hope you understood that. The other kind is the parallel drainage pattern. So parallel, from the name itself, instead of this acute angle tributaries, it is more or less parallel in nature. So you have these parallel. So it is formed on a sloping surface. Of course, if it has to be parallel, it needs some kind of gradient. Therefore, parallel drainage pattern is mostly found in sloping surface. The tributary streams tend to stretch out in a parallel fashion, which I just said, following the slope of the surface. And this mostly happens in a homogeneous terrain, which is quite same, not quite, it should be same. Then the river will flow in a parallel fashion. So we have the dendritic pattern, then we have the parallel pattern. The other type, third type, is the radial drainage pattern, in which mostly develops around a central elevated point, like volcanoes, you can say, or a mountain. You can. So it's basically the river is from here. It is just in this manner. So from one point, it is radially going out. Okay. So that is why we call it as radial drainage pattern. Then we have the rectangular one, which is found in regions that have undergone faulting. So rectangular means what? At 90 degree it is coming and joining, instead of this like it's kind of like the dendritic one, but here, because of the presence of faulting, undergone faulting, that region. So because of that, the streams follow the path of least resistance and concentrated in places where exposed rock is the weakest. So it's marked by the 90-degree sharp bends. It's kind of rectangular. That's why it is named as rectangular drainage pattern. So that is the fourth type. Then we have the trellis drainage pattern. So trellis is what? It is found in folded topography. So if you are asked to explain a different kind of drainage patterns, you can just name all these things. Or if you are asked to differentiate, so in all the cases, first talk about in which area these are mostly found. So trellis, we find it in folded topography, where you find, folded means such terrains, fold kind of thing. So the main channel resides in the syncline or valley, while the tributaries end at sharp angles as they come down the sides of the parallel ridges. So if you take a look at this, here you can see, okay, so this is the main channel, and then the tributaries are joining from this sides. So that is trellis. Then we have annular, where streams flow in a nearly circular or concentric pattern. So all these cases before, we had seen the streams flowing in a straight kind of thing, not straight exactly, but definitely not circular. But in annular drainage pattern, the stream flows in a circular fashion. And that band is formed, circular band is formed because that rock is weak in this particular area. So river is flowing through that weak area. It looks like a ring. So that is regarding the drainage patterns. So we have discussed what? 6 kinds of drainage patterns. The first one is dendritic, then we have the parallel, then we have the radial and rectangular, so and then we have the trellis and the annular. So these are different types of drainage patterns. Now that all the streams, like they'll have a major stream and then they have a tributary coming. So that whenever you're studying about a particular river, you will always study the stream order. So that is a number which is used to indicate the level of branching in a river system. So for instance, you are studying about river Yamuna, or let's say river Ganga. So then you need to understand how many streams are joining this particular river, and how branched this river system is. So we are like, if you consider the Stoller stream order, so stream order is a dimensionless thing, that is just a number indicating how many streams. So for instance, if two streams of the same order merge, the resulting stream is given a number that is one higher. If two rivers with different stream orders merge, the resulting stream is given the higher of the two numbers. So what essentially they are saying is that, let's say this stream is coming, that is given as the number 1, and this stream is given number 1, and they are merging together to form another stream, which, since these are both same numbers, so the resultant stream will be the sum of that. Okay, the resulting stream is given a number that is 1 higher, not exactly the sum. Basically this is 1 and this is 1, so this will be 2. If this was 4 and this was 4, this would have been 5, like that. And if let's say this another example, let's say this is 2 is coming, 3 is coming, and when it merges, then the bigger of this 2 will be the number for the next one. So this 2 is there, 3 is there, 3 is higher, so the resultant stream will be 3. So if you are given a question in which they are asking you to find the stream order, so the based on Stoller stream order method, this is how you have to determine it. Then we have the bifurcation ratio. So the ratio of number of the stream segments of specified order and number of streams in the next higher order. So this is again like stream order, it is dimensionless. So here if you see, it is the ratio of number of the stream segments of the specified order and the number of the streams in the next higher order. So here if you see, let's say we are considering, okay, we can consider 2. Okay, so here if you look, we have 3 such segments which has the order 2. Okay, so we have 2 and the number of segments is 3. So the bifurcation ratio will be number of stream of segments of okay, so the thing is, you have 1 over here, right? The previous one. So 1, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the segment number of segments having order 1 is 10. And the segments having order 2 is 3. So the bifurcation ratio will be 10 by 3. So that's how the number of segments of the previous order by the number of segments of the just the next one. So that is 3. If you look at the next one, you can see order 2 is segments is 3 and order 3 is 1. So the bifurcation ratio is 3 by 1. Is that clear? How we are determining the bifurcation ratio? This I had taken directly from the lectures. So if you have any doubt, you can just ask me. Okay, so higher bifurcation ratio indicates short time of concentration and the probability of flooding will be high. So if you have a high bifurcation ratio, like with respect, like that is kind of relative, but if you have a high bifurcation ratio, then that tells you that the time for concentration is less and the probability of flooding is high. So bifurcation ratio is a very important topic. You have to because in this floods lecture, this is an important part. So just keep in mind. So an elongated basin, that is what we have. Let's say this is A and this is B. So A is elongated basin and it has a high bifurcation ratio. will have a smooth hydrograph. Hydrograph is basically the distance versus time. So this is the hydrograph. So it will have a smooth hydrograph, while a rounded basin like this B with same area and low bifurcation ratio will have a narrow hydrograph, suggesting higher discharge. This is basically, it has a longer time to flow, but here it spreads out a bit faster. So discharge is a bit faster. That's what. So this can be explained by the greater time lag for water to reach the outlet in the elongated basin as compared to the rounded basin. So this distance is more, right? Here it is less. So because of that, this will take a longer time. So it has a longer time to spread out, but here it does not have that much time. So although the bifurcation ratio might be less, the discharge would be high in this scenario. So the shape of the drainage basin is also important. Then comes the recurrence interval. So the name itself tells you, right? Recurrence is what? Repeated, how often the flooding can happen. So suppose the record of maximum mean discharge by a particular stream has been kept for n years. So let's say the mean discharge uh, for each year, like we are keeping it as n, each of these yearly maximum discharge can be given a rank m. So rank is m and the number of years is n. So rank 1 means that maximum discharge has occurred in that particular year, and the recurrence interval can be calculated as r is equal to n plus 1 by m, where n is the number of years you have the record. Like as I said, no, like in previous ones, like paleoseismology or in like old volcano events, like that, people will study the flood events that has happened over a period of years. So that how many years worth of data they have, that is regarded as n, and m is the maximum discharge, like the rank given for the maximum discharge. So if for example in this case, if let's say 25 years, the maximum discharge was recorded in 1965, and then if that is the case, then the year 1965 will be given the rank 1. Okay, so in that case, the probability of such event in the next when it can happen, that is given as n plus 1. So n plus 1 is what? 25 years worth record you have, right? So 25 plus 1 by 1, where m is the rank, so 26 years. So if you want to find the recurrence of similar flood, let's say that occurred in 1971, which has a rank of 7, then the recurrence interval is 25 plus 1 by 7. So that is 3.71 years. So the recurrence interval for such high frequency similar to 1971 is 3.7 years. So every 3.7 years you can expect a similar flooding event. Is that clear, or should I repeat it again how it is found? Only thing you have to keep in mind is the values, that is n and m. So n is the like record for maximum mean discharge, so that is let's say 25 years, and m is the rank which is given. So the maximum discharge is given as 1, and then accordingly it will increase. So increase in the sense that the maximum discharge is 1, and then with the decrease in discharge, this number will increase. So in this particular case, they have given the example that 1971 has a rank of 7, and you have 25 years worth of record, which is n. So the recurrence interval is 25 plus 1, that is n plus 1 by m. Here the m is 7. So when they calculated it, they got it as 3.7. I hope that is clear, but if you want me to repeat, I can repeat it again. Okay, so then we can move forward. So here we are discussing the flood management. So how flood can be managed, because flood is inevitable, like it is a natural process, and now because of urbanization it has become a kind of a man-made process too. But then it will definitely happen. So we need to know how we can manage it so that the loss to life and property can be minimized. So that can be divided into three. The first one is hard engineering techniques, soft engineering techniques, and administrative measures. So hard engineering techniques is by building dams and embankments. Building dams and embankments will help you to restrict the flow, but at the same time you have to keep in mind that the proper uh, measures needs to be taken while opening and closing of these dams. Otherwise, because of this dam failure, flooding can happen. Then levees, building levees. Levees are basically, if this is a river channel, so these elevated portions on either side of the channel are known as levees. So they can be natural, but at the same time, people can build the levees, artificial levees, in order to contain the flow. So that is another thing. Then similarly, wing dikes are there. Then detention tanks. These are all just examples which sir had mentioned, so I'm just giving it here. Then channel straightening. So these are all external factors that you can do in order to manage the flood events. So this is hard engineering techniques, like some manpower is required to do all these things. Soft engineering techniques are afforestation, so basically planting a lot of trees, river restoration, like giving it path to flow so that it doesn't overflow. Wetland restoration. Wetland is basically people who live near coastal areas, mangroves, right? So presence of mangroves helps to contain flood. So such wetlands needs to be restored. Watershed management, flood risk and vulnerability analysis, like how we looked, right? Recurrence interval and all. So you need to know all those things and plan accordingly. So these are something which are done needs to be done physically, while administrative measures is basically what, when you have a lot of rainfall, so then people need to expect a flood. So the administration needs to warn them regarding the flood. Then rescue and evacuation. So if in the event of a flood, the administration should be equipped to do the rescue and evacuation, like arranging boats or like helicopter things, all those things. So that those all come under the administrative measures. Then enforcing the floodplain zoning regulation. So that like people living near the floodplain, so they need to know how far that flood waters can come. So accordingly, administration should take measures to move people away from such regions. Flood proofing, basically like doing these hard engineering and soft engineering techniques, like it's their responsibility to ensure that that area is flood proofed. So I have a video showing these flood management techniques, so you can just watch it. So here you have a reservoir and the water is flowing from the dam. So these are the artificial levees. Oh, sorry. Okay, let it play. I'm just okay. So you have the reservoir on the other side. Then it is dammed, and artificial levees are built on either sides, which is shown over here on both sides. So here the water flow has increased. The level of water has increased. But because they have constructed this weir and this bypass area, so the extra water can flow into that region, thereby preventing the flooding of the entire area. If this structures were not present, then that area would have flooded. So they have constructed levees, they have constructed dams, and in the event of higher water level, they have created the bifurcation path, or bypassing channel. So because of that, the higher whatever water is there, that can move through that particular channel. So now I have just, I think, few 5 questions maybe. So we'll just look into the problems based on this. Uh, which one? Dredging is basically uh, increasing the depth of the channel. So the essential thing during flooding is to increase the channel capacity, because flooding happens when the water is so high, like water flow is so high that it is exceeding the channel capacity. So by doing dredging, dredging is basically creating more space for the water to flow. Yeah, that comes under that that first I had told about this, no, the hard engineering techniques. So that is that involves a lot of like engineering involved. That is why we say it as hard engineering, while soft engineering techniques are something which you know it doesn't require a lot of manpower. Like you just have to know what needs to be done, and that can be done. But hard engineering techniques involve a lot of machinery and everything. So the levies you had seen in this, no? I maybe next class, if I get some images or videos of these flood management thing, I'll include it. We'll have one more session on 19th, that will be like wrapping up the entire course. So I'll be summarizing everything, and maybe we can discuss some problems also. So it will be helpful for your exam. It's not uploaded. Oh, okay, okay. I'll just verify it. Okay, I'm sorry. I'll just check that. I'll upload it to, with along with today's. Okay. Okay, so the I'll go to the problems then. So the first question is, the Kedarnath flood of which year, that is what I'm asking, dash, was due to dash, which led to excessive number of casualties and property loss. So based on the things which we discuss right now, just give me the answer. So when did the Kedarnath flood happen, and why, how, like what was the reason for that flood? 18 नहीं था. It was a devastating flood, like or can you just let it like leave the year? Can you tell me why it happened? Like what was the cause of that flood? Yeah, yeah. So it was due to cloudburst. So yeah, because the thing is, if you know, like we discussed right now, upstream flood and downstream flood. So what happens is that uh, now this okay. So Kedarnath is in a higher altitude area, right? So like people trek and go there. So that is kind of in the upper stream of that river, like upstream part of the river. So what happened is that the because of cloudburst is what, torrential rain for a brief period of time. So it happened like in a few minutes, but then it was very devastating because a lot of water came down all of a sudden, which led to the excessive number of casualties and property loss. And this happened in 2013. So the answer is 2013, and the reason for Kedarnath flood was cloudburst. Okay. So the next question is, as the river carries sediments from source to sink, what happens to the particle size? Like, debris flow is a type of landslide, right? Cloudburst is like, because of cloudburst, debris flow is a type of landslide or flow or mass wasting, you can say, in which what happens, a lot of water, when a lot of water is coming, because of that it brings a lot of this earth materials like rocks, soil, all those things. So cloudburst uh, causes debris flow. It's not that cloudburst and debris flow are same. Like cloudburst is an event in which you have a lot of rain for a very short period of time, and because of that a lot of water coming in, so that can take a lot these like soil materials, uproot vegetation, rocks, all these things, and it can come down as debris flow. So this Kedarnath flood also, like along with the flood, multiple regions experience this landslide events also. So like basically cloudburst is the cause for the flood as well as the landslide. So do you know this? As the river carries sediments from source to sink, what will happen to the particle size? Sediment particle size. Uh, so just can you tell me like why, or from whatever I had said, like why did you say it decreases? Yeah. So what will happen is flow will be different, right? When it is in the upstream part, like when it is coming from the source, initially its flow will be very fast, like velocity will be very high. So in that region, it will be able to take all these big materials. But as it comes down, what happens? The flow will gradually decrease because the slope is also decreasing. So as a result, the particle size will decrease. Okay, so just keep in mind, like from source to sink particle size decreases. The reason is what I just said. There is a change in the slope, there is a change in the flow velocity, and as you said, the carrying capacity. The next question is, when the river debouches into the plain, the sediments get distributed and forms what? So like the river is coming from a slope, and then when it reaches the plain area, what is formed when the sediment is getting deposited? Yes. So answer is alluvial fan. So what happens, if this is the mountain, let's say from this area the river is coming, so this is a slope area, and when the river deposits at this region, it will deposit in the form of an alluvial fan. Which part of the alluvial fan is highly risky and which is less risky? Like this is the head and this is the toe. So which, not head, you can say apex. So which region is more hazardous and which is less hazard prone? I had shown an image, no? Just kind of recollect it and tell me. No, no, I'm asking, like, you have the fan, no? So which part of the fan experiences the most, like, which is the most hazardous region and which is the less hazardous region? Like, this is the apex and this is the toe. So in which direction the hazardous nature decreases? Like that you can tell me. From apex to toe or toe to apex? Just try to recollect. I had shown an image regarding this. Sorry, I didn't hear. Can you tell me? Okay, so like I'll be uploading these slides so you can verify that again. So the answer is that it will be from the apex to the toe. So in the apex will be the most hazard prone area, and towards the toe it will be less, because it is just all of a sudden from that slope the material is getting deposited. So the initial deposits will, over here, as you go from the apex to toe, the material become more finer, so all the big materials will be dumped over here. So that's more hazard prone. Now next question is, dash are the natural boundary for river which prevents overflow onto the floodplains. Not terraces. I just showed you, like, people make artificial ones, and also naturally also it forms. Yes. So it's not terraces. Terraces is basically when the river level changes, right? So for instance, let's say the river was flowing like this. Okay, the river is flowing in this direction. So it was flowing like this. Now, if suppose the what happens is that where the river is flowing, it will erode, right? Now let's say water level decreased or water inflow decreased. So then what will happen is that the river will flow. Oh, okay, sorry, not this one. So the river flow will become something like this. So with the change in water level, the river terraces are formed. But here, what I'm asking is the natural boundary for the river, which prevents the overflow onto the floodplains. That is basically like if you have a river channel like this, then it should have some embankments on the both sides, which will prevent the water, that effect of water overflowing. So the answer is levees. So here you can see, before flood it is like this. During flood stage water level, what will happen is the material will get deposited like this. So thickest and coarsest sediments will deposit on the channel edges. So because of multiple flooding events, these will be formed, and in future flooding events these will kind of act like a barrier. So levees are the natural boundary, and now artificially also people are building levees to manage the flood events. So that is regarding the flood part. Now I also have slides of the tsunami part. Maybe we can just start it. And I don't think I'll be able to finish the entire topic today. It's already 7:40. So maybe next, that last session, we'll discuss few remaining points from the tsunami, and then we'll wrap up the entire course. Like we'll discuss the entire course. I'll summarize it, and then we'll have some problem solving. So shall I move on to tsunami, or you want me to do it in the next class? I'm not sure I'll be able to complete it entirely, but maybe I can just start it. And is that fine, or should I do it in the next session? Okay, okay, okay. So I'll just discuss it. Some portion will be left out. I'm sorry, because I have a lot of slides on that. So that we can definitely do in the on 19th. So we have discussed about floods. Now this is another hazard which is related to water. So that is tsunami. So tsunami is mostly generated by earthquakes, like underwater earthquakes, and even there was an instance in which volcanic eruption uh, resulted in a collapse, or the flank of a volcano collapsed into the ocean, which triggered a tsunami. So tsunami as such doesn't happen all of a sudden. It was due to earthquake events, which is mostly the reason. or other mechanisms which are caused by displacement of large volumes of water. So the essential thing is large volume of water should be displaced. So that can be due to either earthquakes or landslides, volcanic eruptions, asteroid impacts. So these are all reasons why tsunamis or how tsunami is generated. And tsunami means harbor wave. So that this name is a Japanese uh, thing where I think su means harbor and nami means wave. So that it is called as tsunami. Because the Japanese they experience all kind of natural hazards, like they frequently experience earthquake events, they have volcanic eruption, they have tsunami. So it's like, because of this the Japanese engineers have very well maintained that area in order to face these kind of hazards. Like they know, they have managed it really well. So, as I said, tsunami can be generated by multiple factors like earthquake, landslides, and all those things. So, first we'll discuss about the tsunami generated by earthquake. So, what happens? Displacement of large volume of water during shallow focus underwater earthquake associated with the sudden rise or fall of the seafloor. So, underwater earthquake, when it happens, a lot of water, a large volume of water will get displaced or moved. So, when that huge amount of water is displaced, that will generate a tsunami. This is mostly associated with displacement due to reverse fault movement on subduction zone. That much detail I don't think you need, but you just have to understand that underwater earthquakes trigger tsunami. So, most of the tsunamis are associated with earthquake events as a result of movement along the reverse fault, and occasionally earthquake happening on normal faults can also trigger a tsunami. uh, but tsunamis as a result of strike slip fault movement is not very frequent. So you remember what rivers and normal faults are, right? Can you just tell me what a reverse fault movement and what a normal fault movement is? Just I'm just trying to refresh your memory, that's all. What happens during a reverse fault? Okay, so reverse fault movement occurs when the hanging wall moves up relative to the foot wall, and the opposite happens for the normal fault. That is, hanging wall goes down or the footwall moves up relative to the hanging wall, like that. Okay, this I'm just recapping what I had told in the earlier classes. So the two plates move at a nearly constant rate. However, the boundary between the two sticks for many years. Okay, so plate boundary, you know, right, between two plates. So although both plates are moving, that boundary will stick for a longer period of time. I'll just see if I have an image. Okay, I didn't keep an image. Okay. So the continental edge gets pulled downward and towards the continent as the oceanic plate moves under it. Uh, so this is basically, I'm just explaining. Okay, over here I have. This image will be sufficient. So we have a subducting plate and we have a overriding plate. Okay, so what happens here is that this particular region, that boundary region, gets stuck, and this area slowly gets distorted because the movement is not very even. So it becomes a bit higher, and when the stuck area ruptures, so you can see this depth difference, right? Here it is a bit shallow, but here it has become deep. So when this ruptures and causes an earthquake, that will displace a lot of water, and that lot of water is basically the tsunami. Tsunami starts during the earthquake, and then the waves will spread in both direction, like towards the land and towards the sea. This is what is happening. So between earthquakes this is happening, and then during an earthquake and after minutes later this is what is happening. The height of the tsunami wave, it depends on the magnitude of the earthquake, like how strong that earthquake is, the rupture zone area, like how far that rupture has happened. So you need to refresh your memory regarding the earthquake part. Okay, that's what I'm repeating over here. So the rate and volume of water which is displaced, and the depth of water above the rupture, which you had seen in this diagram also. The depth of the water has increased in the second figure, right? So if the depth of the water is higher, then more water will be displaced. Size of a tsunami in the open ocean is related to maximum displacement on a fault. So compared to the normal fault, the reverse fault movement might have greater offset but less vertical displacement of water due to its gentler dip. So if a tsunami is formed as a result of movement along a normal fault is more steeper. Okay. So because of that, more water can be displaced. So compared to a tsunami triggered by a movement on normal fault, the tsunami generated by movement on a reverse fault will have lesser water displacement. So height might be a bit lesser, size might be less. That is regarding tsunami generated by earthquake. Then we have tsunami generated by volcanic eruptions. So water can be driven upward or outward by fast moving flows of hot volcanic ash. So a lot of volcanic ash is coming. So that can displace the water. Essentially, tsunami is formed when water is displaced. So volcanic eruptions, they can displace the water, either by fast moving flows of volcanic ash, or submarine volcanic explosions, like underwater volcanic explosions can happen, or the collapse of volcanoes in a landslide. That is what I had mentioned as an example. A side of the volcano, when it collapsed into the water, that displaced a lot of water and resulted in a tsunami. Tsunamis generated by volcanic eruptions are poorly understood. Like most of the tsunamis are associated with earthquake events. So these are a bit rare, because of which they need to be studied more in order to understand like how they are generated, or like how volcanic eruption is causing the tsunami. And because they are not very frequent or very common, so their maximum size is not well known like the ones generated by the earthquake. The height of the tsunami depends on the volume of mass displacing the water and the height of the fall. So how high that tsunami will be depends on the uh, volume, that amount of water that has been displaced, and from which height this landslide or rock falls have come. So if they came from a huge height, then they can displace a even higher amount of water. But if that fall is very gentle, then that much of water will not be displaced. Submarine landslides also generate tsunami. So the only thing you have to understand is, uh, so far we have discussed earthquake generated tsunami, the volcanic eruption, and the landslide. In all these three things, you have to understand uh, these three events can happen underwater also and from on the outside also. Both can trigger a tsunami. Then the one which I had said, tsunami generated by volcanic flank collapse. So occasionally in regions like Hawaiian Islands. So if you remember, the Hawaiian Islands are what? Hotspot volcanoes, right? So the Hawaiian Islands or the Canary Islands in the Atlantic Ocean, what happens is these old volcanoes, which or not just old volcanoes, like they're basically islands, right? So the if the volcanic flank collapses and slides into the ocean, that can, because a huge mass is coming and that huge mass is displacing a lot of water, so that can generate a tsunami. So this results in the sudden displacement of thousands of cubic kilometers of water and generation of tsunamis that can be hundreds of meters high. So you have to imagine how high that is, right? Hundreds of meters is not such a small number. Then we have tsunami, which is generated by asteroid impact, which is very rare. But if an asteroid comes and hits an ocean floor, that can displace a huge amount of water, which is capable of creating a tsunami, which is really really big. So you can say a mega tsunami can happen, right? So this is not very frequent. So it can happen one per million years. So millions year scale, this can happen. But if it happens, that will be a big big tsunami. It's not going to be the normal uh, like dimension. So I think I'll stop over here because the next is a new, not a new topic, but a bit more you have to see. So that we can discuss in the next session. That would be better so that I can start it afresh. Is that okay?
Okay, okay, ma'am.
Okay.
Ma'am, what destructive tsunami?
Huh? Mm, see, like the most common tsunami that you see, like in news and all, you're seeing, no. So that most common ones happen in this shallow zones, like by reverse fault movement, and such tsunamis are like tsunami as such. It is big, but they might not be very massive. Massive tsunamis happen in case of that is actually dependent, you can say. So because if you remember, uh, I had shown you an image, no? um, yeah. So it's kind of dependent on this thing, that is, here you will be having a reverse fault movement, okay? So this is the overriding plate, this is the subducting plate. So that like the scale of tsunami, how massive it is going to be, depends on the depth which is over here. So you can see this depth. So if even in a reverse fault, if this depth is going to be more, then a lot of water is going to be displaced. So as a result, you will have a massive tsunami. But the primary thing that we can say is massive tsunami can be generated by a movement along a normal fault, or the one which I just said, the asteroid impact. So asteroid impact can actually cause a mega tsunami, which will be more, the height will be really really high, and it can cover a large area. Like for instance, the 2004 December tsunami, that uh, like that was not a mega tsunami, but even then it covered many areas, right? In Andaman it affected Lakshadweep, the southern coast of India, so it covered a huge area. So if a mega tsunami happens, that will go even further. Is that clear, or you still have doubt? Hmm. Hmm. Yeah. Huh. Yeah. Most of the tsunamis that we see are a result of this reverse fault movement in the subduction area. This is very common. The other ones which I was talking about is not as common as these events. Like those are also triggering tsunamis, but the common tsunamis that you see are as a result of this subduction zone earthquake. I'll discuss this in detail in the next classes, like next class. More technical things are coming up. That's why I stopped today because it will be too much of information. Okay. So I'll just stop sharing. Um, So, before the next session, if you want me to focus on any particular topic or which you need help with, you can just maybe uh, you can just mail me if that is okay for you, or you can just put it in the discussion forum, so I can look at it and then those topics I can discuss, because that will be the last one. So if you want any particular topic to be discussed more, or if you need any help with anything, you can just put it there. Okay. Yeah, I'll put my mail ID in the chat box for your reference, so that way you can contact me in just a moment. I'll just keep it. Okay, so I have put it in the chat, so you can just note it down and you can mail me if you have any queries. And I'll include that in the next class. Lecture notes, you mean the PPT? Like the PPT I'm sharing in a Google link, Google Drive link I have shared, and I think that will be available for you. So that will be there. Okay. So shall I conclude today's session? Yes, yes, I'll do that. It's thank you for reminding me. I think I might have forgotten it. Okay, I'll do that. Okay, thank you. You can leave the meeting. Okay.
Thank you.
Okay, thank you.